Welcome back. So we were talking about tuning learning rates, and we talked about a bunch of approaches, namely decaying the learning rate, maybe jointly tuning learning rate and batch size, and also we talked about warm-up. There's another method I want to talk about, and that's called cyclic learning rates, or cosine annealing. It's called sometimes in the literature. And this is actually a very interesting idea in terms of the schedule you use for your learning rate. And the idea is that you're not decaying the schedule necessarily. You're actually using a periodic function to determine what your step size or learning rate should be. That's why it's called cyclic learning rate. So you start, let's say, with a large learning rate, you reduce it, and then you suddenly again use a large learning rate again, reduce it, and you continue doing this process. For instance, one of these, a simple way to talk about this is through what I mentioned. It's called cosine annealing, that the learning rate in each time, or in each epoch, if you will, is a cosine function, okay? So it has some minimum value and some maximum value, and it alternates between these two minimum maximum value with certain frequency, okay? Now, what we typically also do in practice is that we use this in conjunction with other methods. For instance, this n-min and n-max could themselves be tuned by using a decaying learning rate schedule. Even the frequency itself could be decayed. Okay, so this is like a general way of thinking about this approach. So I have this max learning rate, and I'm going to basically use this cosine function to reduce the learning rate to the minimum value, okay? And then I'm gonna increase it. But I'm not gonna increase it up to learning rate max anymore. I'm going to use a decaying schedule for learning rate max. So I'm gonna reduce it to this point, okay? And then I may optionally also increase the time it takes for me to go from a high learning rate to a low learning rate, and vice versa. I hit the minimum learning rate again, and then I go back, reset everything, okay? And then I continue doing this process, okay? So the idea is that by doing this, you are basically resetting the model, or basically that's how one could interpret this process, okay? So every time you're doing this reset, such that hopefully by doing this reset, you're resetting the training process, but from a better starting position, okay? So here I'm using a random initialization, as we talked about, for instance, the Javier initialization to initialize my model, and then I use this schedule to quickly find a better initialization. Then I reset my training process using again a large step size, large learning rate. Now with this better initialization, find another hopefully better initialization, and I continue doing so until I converge to a good solution, potentially faster. Okay, and this approach has been proven to be very effective in a lot of deep learning optimization tasks. Okay, so my hope is to actually dissect this approach and provide maybe a more formal explanation of why this approach is going to be helpful, okay? And also what's the connection, the intimate connection between this and the constant step size that we've talked about before, okay? And my approach is actually to define what I call multi-step risk, okay? And as we'll see, a constant step size is basically something that tries to minimize the one-step risk, but a cyclic step size schedule is something that tries to minimize, let's say, the n-step risk, where n basically determines like how many learning rates you use in each period. Okay, so let's see how we can arrive at this conclusion. Okay, and obviously we're going to work with a simple function to basically make this connection apparent. All right. So let's consider this scenario. Let me give you a function, loss landscape, and then let's say that I'm currently at WT. So WT is one point in the landscape. Okay. Now there are two bad things that could happen, I would argue, in the immediate next update. So I'm going to go from WT to WT plus 1, and during this process, two very bad things could happen. Okay. First of all, it could happen that I'm currently in a very flat landscape. So WT is in a very flat landscape. And in order to go from WT to WT plus 1, I'm using a very, very small learning rate. Okay. So why is this a bad thing? Because it means that I'm gonna make a very slow progress. So because a step size is small, landscape is flat, I'm going to barely move. Okay. Now let's consider another bad situation where WT is instead in a steep landscape, okay, very sharp landscape, and we are using a very large learning rate. Okay. Why is this bad? Because it could lead to divergence. Okay. So here is my attempt to visualize this. So this is the first case. This is WT, and then use a small step size to converge to go to WT plus 1. So you barely move. On the other hand, if you are here, if you are, let's say, here in a steep landscape, let me use a different color. And if your step size is large, you may actually jump to the other side. Okay, again, you are a steep direction, a steep landscape, you use a larger learning rate, and then you're going to diverge. So this is, let's say, WT, WT plus 1, and then WT plus 2. Okay. Now this is bad, but I think it's also intuitive to have a comparison between these two bad cases, right? I argue the first one is bad, but the second one is terrible. Okay. So first one is just saying that the progress is slow, but nonetheless you are making progress. Second one, on the other hand, says that you may actually diverge, right? So you may not necessarily make a progress. So this is what we want to hedge against. Okay, so essentially with a constant step size, we can only hedge against one of these, right? So regardless of whether the landscape is flat or steep, we have only one choice. Okay, so I can only hedge against one of these. Which one is wiser to hedge against? I would say the second one, right? Because the first one, again, we still are making progress, but the second one is terrible. Okay? And this is exactly what happens, right? That the constant step size is basically going to look at one step risk, what will happen in the next immediate update, and tries to minimize that as best as possible. Okay? And by minimization, it's going to hedge against the second case. Okay? But cyclic schedule, on the other hand, minimizes a multi-step risk. For instance, what could happen in the nth step from now, and let's try to minimize the risk of that. Okay. All right. So I've been talking about this risk. Let's see what I mean by risk. And to do that, I'm going to consider basically a very simple optimization algorithm and a very simple function that we want to minimize. Namely, let's consider gradient descent. There is no stochasticity or anything like that here, right? And also let's consider a convex quadratic loss, okay? So without loss of generality, I'm going to assume that the loss is gonna look something like this. Q is the Hessian, okay? I am assuming that it's a strongly convex function, so the Hessian has a minimum eigenvalue, which is, let's say, mu, and also this is a smooth function. The Hessian has an eigenvalue which is bounded by L. Okay, and also it's not too difficult to see that the optimum solution is 0. Okay, and this is again without loss of generality. Now, what's the gradient descent algorithm for this function? Again, gradient descent. Just let me write it here. WT plus 1 is WT minus eta, the gradient of the function at WT. Okay. So therefore, we're going to arrive at this update. W plus is my update. So I'm going to go from W to W plus using this this update, which again can be derived quite easily by noticing that the gradient of f, let me write here, is simply QW. So you just plug that in this formula and then factor out W, and then you can arrive at this formula. All right. So now let's consider the one-step risk. Okay, and by that I mean the following: how much progress I'm going to make by updating my parameter using gradient descent relative to the progress that I had made when I'm currently at W. Okay, so, and by progress here I mean the difference between my update W plus and the optimal solution W star relative to the difference between W, the current solution, and W star, the optimal solution. Okay, so this is our risk, and this will be a function of layering rate, eta. Okay, so in this case things are very simple. So W star is actually 0. Okay, so we are talking about the norm of W plus and the divided by norm of W. So I know what W plus is. I plug it in here. Now this is again from linear algebra is basically it's called the operator norm or the maximum eigenvalue. So this will be nothing but the maximum eigenvalue of this matrix. Okay, and again this is there are going to be two cases here, right? So either what I have inside this identity matrix minus eta q is positive definite, okay, such that the maximum eigenvalue is going to be 1 minus eta mu, or this is negative definite. So therefore the maximum the magnitude of the largest eigenvalue is going to be L times eta minus 1. Okay, so I would say it's not very important for us, but after certain very basic linear algebraic concepts, we can show that the one-step risk is going to be given by this formula, and it only depends on the learning rate. So this is our decision variable, and also mu and L, which are the strong convexity constant as well as the L smoothness constant. Okay, so now we want to, as we discussed, we want to find the learning rate that minimizes the one-step risk. Okay, such that we hedge against those two bad cases. Okay, it turns out that therefore we want to solve this optimization problem. This is actually an instance of a linear program, and we can actually find a solution quite easily by exploring where these two linear lines intersect. Okay, so very simple. But again, it's not, I would say, very important. But if we do this, we can find that basically the best constant exercise that minimizes the one-step risk is going to be given by 2 divided by mu plus L, such that when mu is exactly equal to L, this becomes 1 over L. This is exactly the learning rate we derived for gradient descent early on in the course. Okay, and so the point is that this learning rate can actually be directly calculated by analyzing how gradient descent performs on a strongly convex and L-smooth functions. But we derive it from a different perspective. We derive it from the perspective of minimizing the one-step risk. Okay, so therefore, the learning rate that minimizes the one-step risk is exactly the best constant step size that we can derive in classical convex optimization literature. Okay. All right. So now we want to generalize this idea. Okay. So let's say instead of the one-step risk, I'm actually interested in two-step risk. Okay. So let's say that the current solution is W. I'm going to update that using gradient descent to go to W plus, and then I'm going to update W plus using gradient descent to go to W sharp. Okay. So now here, when I'm updating W to W plus, I'm going to use learning rate eta plus, and when I'm updating W plus to W sharp, I use a learning rate that I call eta sharp, and these two are not the same. Okay, otherwise we would get back to the previous case. All right, so therefore what's my goal? My goal is to find these two learning rates that jointly minimize the two-step risk. What's the two-step risk? It's again the relative amount of progress we're making compared to the current solution. So therefore, because I'm talking about two-step risk, what will happen 2 times from now, I'm going to be interested in the norm difference of W sharp and W star relative to the norm difference of the current solution and W star. Again, W star is 0 without loss of generality, so we are talking about this ratio. Using, again, very basic linear algebraic techniques, we can show that this will be a function that's like this. Basically a quadratic function, if you will, okay? Now, this again can be solved, but it's not as easy as a linear program, like in the previous case. But nonetheless, you can solve it using an approach that we call leveraging Chebyshev polynomials. So the main idea that we are interested in is that the reciprocal of these learning rates are basically solutions to a quadratic equation. Okay, so they are given by this and this. Now, as you can see here, they are not the same. They are different, and this also is suggesting that if you are interested in minimizing the two-step risk, you should alternate between the selection of these 2 learning rates. For instance, you use this one and then that one, or the other way around. It doesn't matter. What matters is that you should alternate. Okay, and the idea is that by doing this, you are hedging against not just the bad case that you were in the steep landscape and using a larger step size, but you are hedging against both of those cases. Okay, so this is basically very, very interesting. So it makes sure that you are avoiding divergence, but also you are making a lot of progress, especially in the regions where the landscape is flat. Okay. So hopefully this gives you an idea of why we may want to use cyclic learning rates, but there's a sort of I would say a caveat. Our analysis here was based on, again, gradient descent. It was based on minimizing arguably the nicest function in the world, which is a convex quadratic function. Are these idea like transferable to more difficult learning settings? That's actually a question that remains to be open. Nonetheless, I would say this is a good segue to our next module, which we're going to start talking about advanced training algorithms. Instead of, let's say, resorting to heuristics to, for instance, tune the learning rate, is there a way to do that in a more principled way? Okay, and also, what are some other ingredients that we may potentially want to use in our SGD algorithm to make sure that we make progress faster, we find higher quality solution, and also we find models that could potentially generalize better. I'll see you next time.